Right, so welcome everyone again. We were here on Monday and we've talked about large language models, and we mostly talked about what's out there and how they've evolved over time. Today, it's going to be more about how to actually use them. So just repeating now for the recording, the slides, I'll try to upload them always before the lecture, because I think some of you would like to take notes on them. Regarding the recordings, I'll try to update as regularly as I can, but we're having some software issues, so it might be that sometimes I upload 2 lectures at once. You'll see. But definitely, it's not going to be too late. Yeah, so let's start with the second lecture of the first block. And so we've probably seen last time there are so many transformers out there that it's really even hard to start and say, okay, which one is the best for the task? Generally, as a rule of thumb, the newer the better. And probably also we've looked at masked language models, we've looked at autoregressive models, alternatives that are coming up, and each one of the types has pros and cons, also in terms of dimensions that you need to consider. But today is more about, we have these huge language models. How do we use them effectively? I mean, they are way more powerful than the classic pipelines with LSTM that we're used to design, but only if we are able to use them in a more efficient way. Because of course, no one here is going to actually train GPT-3 from scratch. And that's what today is about. So just to get a few terms defined, when I talk about fine-tuning, I mean that we take a pre-trained model and we're going to retrain, well, usually part of it, although considering the definition could even be the entire model, to use the overall learned knowledge that he has for a specific downstream task. So, for instance, BERT has been trained on, well, all the text data for language modeling, and then we fine-tune it for a specific task. So that's what fine-tuning means, to retraining for a downstream task with usually less data. And then a term that you will hear a lot is called few-shot learning, which is a subset of fine-tuning and just means to do fine-tuning when you really don't have a lot of data. And when I say not a lot, that could mean anything between 1 or 2 data points to a couple of thousands, which is still nothing compared to an entire data set. Let's say the slightly more official definition is the n-way k-shot learning, which means we have n classes and then we have k instances, meaning how many data samples we have available. Most of the cases you're gonna only see k-shot learning, n ways usually left out in the field. And so, for instance, k can take any value, for instance, as I said, even 0, meaning that when you just use a model without, you just use it for the downstream task without doing any refinement. Okay, so what's the motivation for fine-tuning? Well, as I said, it allows us to make use of these massive language models that we have available. So far we've seen that fine-tuning large language models has much higher performance than creating a model for the task specifically. It does converge a lot faster because you can leverage all the general knowledge that the model has learned at pre-training. It's incredibly data efficient. As I said, we're going to go from 0 to a few thousands examples, opposed to, we've said, billions of tokens that were needed for GPT-3. And of course, we can see it as a shortcut in effort without losing performance, because I can take the GPT-3 and I can take maybe a couple of GPUs. It's still going to take a day, but it took them years on thousands of GPUs. So the effort that I need is definitely less. The first and most common setting is, of course, the traditional fine-tuning, where all parameters are retrained. So in this case, we have a pre-trained language model on, well, an unlabeled dataset, because it's just next word or masked word prediction. And this is, so pre-trained on unlabeled dataset, and then I have some downstream task That could be question answering, classification, whatever you want. And then when we take the smaller data set for the specific task, we just retrain all the weights. And this is like the standard way things have been done for quite a while. Of course, this is it's really, from a computational perspective, is a high effort, because BERT alone is already like in the hundreds of millions of parameter. So the obvious next step is, okay, can we freeze the weights from BERT and just retrain the layers that are put on top of it for the downstream task? And the answer is yes. And of course, here there are a lot of other parameters that enter the game. For instance, okay, which layers am I going to fine-tune? Also, maybe which parts of the layers, maybe only biases or attention weights. And in this case, you already going down from, as I said, fine-tuning hundreds of millions of parameter, which was the case for BERT, but for other language models, we might even talk about billions, down to usually a few thousands. And these weights are only the weights of the layers they are adding on top. Classical example is you take a BERT, you put usually 2 to 3 fully connected layers on top, and these can already generate a classification pipeline. And if the fully connected layers on top maybe go from the dimension of 764 to 2 directly, the number of parameters that you have to fine-tune is just 768, I think is BERT, times 2. And that's all. Right. But for each task that you have, you will still have different parameters. So even if I have BERT, and then it gets fine-tuned for classification, but then I switch to question answering, I need different parameters, because of course the parameters for classification are not going to work for question answering. And so every time I switch task means I need to ditch the layers that I had before, I need to take new layers and repeat the procedure. And this is where the idea for prompting comes. If you recall from the last lecture, we've said that GPT-3, the main motivation behind it was to switch to this few shot kind of setting where I don't need to retrain the model at all. And this is exactly the strategy that is used to do it. So the solution to not having to change the layers on top is prompting. And how does that work? Well, the whole point of prompting is that I have an objective for the downstream task that I'm tackling, and I need to change that objective to somehow be language modeling. So for instance, if we take an example with sentiment analysis, we have the downstream task, which is going to be take a sentence and classify it either as good or bad. And the language modeling, which is going to take a sentence and it will try to generate the next token or to fill in a gap. So what I can do is, so usually we would have sentence, either predict great or terrible. And then I can take a language model and I can add what we are going to soon call a verbalizer on top. And then I let the language model predict the next word, being that word either great or terrible. Let's go a bit more into details. So for instance, here I have a 3-hour cinema master class, right? And this is a sentence about a movie. And normally the classification pipeline would tell me, oh, class positive, 86%, confidence, class negative, 14%. But in this case, I'm going to attach to the sentence, it was, and then I'll let the language model complete that sentence. Now, how are we sure that the output will be great or terrible? I mean, it could be any other word in the dictionary. The language model just outputs a distribution over the entire vocabulary. So what I do, I just ditch all other probabilities for every other word, and I just check whether the probability for terrible is higher than the probability for great, and based on that I decide what the output is. So in this way we have made sure that now classification, sentiment analysis has the same format as language modeling. There's pretty much no difference. And although the idea for prompting and, well, then few-shot learning was already popular like in 2018, GPT-3 was probably the first model that, by having such a large scale, show that actually language models are good at doing this. Because before it was like, oh, that's a property that we would like to have. It works sometimes, but still nowhere near actually training a model. And of course, if I'm using prompting, then I don't need to retrain any of the parameters, because I'm like, oh, the language model has done a lot of pre-training, is pretty much good at everything. I can just let it continue my sentence. There's no gradient update here. So computational effort for training, none. Exactly. So if I just apply prompting, meaning I provide the sample that I want to get, well, classified or whatever the task is, and then I get the answer by filling in the gaps, that would be zero-shot learning, meaning that I'm doing inference with no examples. So GPT-3 or whatever model I'm using has no knowledge a priori of the task that I'm doing. This is the first instance that it sees. If I add one example, so for instance, here I want to translate English to French, and then I give one example of an English input and a French output, and then I give the English input that I want to translate, and I let it produce the output, this would be, of course, one-shot learning, because I'm giving one example. So the K-shot is literally translated in how many examples I'm providing before I'm asking to perform the task on the utterance that I care about. And so, as you can guess, from there, the term few-shot, which means I'm letting the language model complete whatever I care about by providing a few examples. So these examples that are provided to the language model are called demonstrations. And whenever I'm using prompting together with demonstrations, that in the literature takes the name of in-context learning. And the thing that has been seen quite quickly is that in-context learning is way more efficient than traditional fine-tuning, up to the scale of 100. So fine-tuning on 100 data points can be as efficient on as actually providing one example in an in-context learning setting. There was a question. So few-shot learning just means in-context learning with few examples. Yeah. So just to repeat, there's the overarching term of fine-tuning, which means to get any pre-trained model to do a specific task. Few-shot learning is when I only have a few instances, and usually the way to do it is in-context learning. That's like I think the first way that was proposed. Right. So it's true. I mean, it's what I said earlier, GPT-3 was the first model that really showed high performance at few-shot learning. So repeating the question for everyone, if I agree with whether only large language models are good at few-shot, it has been the case for a bit. There's a bit of a trend on the contrary side of that, but that's like a month, like maybe 2 months old. But let's say large language models were the first ones where few-shot actually worked. And we'll see later there are techniques to have this on also smaller models, but we'll get to that. All right. So a bit of terminology. So we have said we have our input, and then we use language modeling to complete a sentence and therefore get the label that we're interested in. Now, here there are two mappings that are happening. The first one is I want to map my input within a format that the language model will understand, as in, oh, I'm going to perform this task. And then I also need to map the output. So for instance, for sentiment analysis, we know that usually there is positive and negative sentiment. But in that case, it was like, it was terrible, it was great. Meaning that, for instance, my verbalizer, so what maps the output in that case was mapping negative to it was terrible. So just to repeat in this case, the pattern is the function that maps the input to the text. So basically is the template for your input. So sentiment analysis could be review, column, and then the actual input. And the verbalizer is the corresponding thing for the output, for the label. So for instance, for the sentiment, it would be sentiment, column, well, the actual sentiment, or it was great, it was terrible, whatever you'd like to receive. So for instance, here, it would be this is an example with this is a two-shot learning example. So we have two inputs, corresponding output. Both inputs and output have been applied, we've applied the pattern and the verbalizer. And then we have the instance that we care about. We apply the pattern to the input, and then we apply to the verbalizer to the output, which is still masked, and the language model has to predict it. So seeing it a bit more in a formal way, and the reason why I'm trying to be precise here is because patterns and verbalizers can actually play a massive role in the performance of your model. So as you see here, the verbalizer is what's applied to the output, pattern is what's applied to the input, and pretty much zero-shot prompting will look at the max, so among the labels that you care about, so the argmax of y, so basically the label in your label set of what's predicted by the language model depending on the input. And of course, we always take the patterned and the verbalized version of it. When we have instances, meaning demonstrations, aka we're doing in-context learning, it's the same setting, but of course we have couples of inputs and outputs to which we have applied the pattern and the verbalizer. And these are, of course, the demonstration. The prompt, meaning what you request to the model, together with the examples that you provide together with it, basically causes a lot of change in the performance of the model itself. And here we can see, for instance, experiments that have been done with GPT-3, and the only thing that was varied was the prompt format. And so the reasons why we have vertical distributions is because they have done several tests, changing, well, splits. And we see that the distribution, depending on the set, can vary a lot depending on your prompt. So if you change the pattern and verbalizer, you can literally go from a not so well working model to possibly the best performing. And this, of course, raises a lot of question of why does in-context learning work? And why does it work so well at a larger scale? Yes, there is a question. Number what, sorry? 13. What, sorry? Mm-hmm. Temperature. Yeah. Of course. So this would be the case with the temperature of 0. So we're not going to really get into temperature. You probably know it by having played with ChatGPT around. The temperature just pretty much mods the creativity that the model has. And how do you do it? Well, the most basic approach would be to not let the model choose the exact argmax, but maybe choose from the most common words. And the more you give it the freedom to diverge from the argmax, the more the answers, well, empirically look creative. There's, of course, no certainty that it will be just more like creative in the sense that we human mean. All right. Let's continue. So why does in-context learning work, and why does it start to show up only at a certain scale? Well, the examples that you provide, so those demonstrations, it doesn't really seem that they allow the model to learn the task on the fly. So it's not like GPT-3 will learn classification because it has seen this one example. But rather, that example allows GPT-3 or whatever model you're using to locate that task and the information that connect with it within the entire knowledge that it knows. And this is the first hint of why this only works at a certain scale, because the larger the model, the higher the capability of inherently storing information from pre-training, and the more data points I can actually store. So that's why if I have billions of parameters that have learned billions of tokens, then it's more likely that I'm good at locating a certain task, because it's more likely that I have seen it, and I have more memory available. So of course, if the distribution that it has been seen at pre-training time differs substantially by what's contained in the demonstrations, it's likely that it's not going to work out. And that's why also models that are able to do few shot are usually training on like a vast data set, possibly as diverse as you can. It seems like demonstrations are not seen by the model as ordered pairs. It seems that like if we provide an input and the output, there's not a lot of like logical connection. Oh, this is connected to that, but rather everything's taken as terms in order to locate the task within the vast knowledge. And what's quite funny is that, of course, we know that the examples that you provide are quite crucial for the model performance, but even the order, and this is probably just like statistical phenomena that we can't quite explain. It's like the first term that the model will see probably will impact what's the first thing it's gonna sort of look up. And when I say lookup, it's literally just attention multiplication. There's not like an explicit lookup in the weights that it has. And of course, here also the term frequency will count quite a lot, because if my demonstration has a lot of the terms that appear in the pre-training corpus that was used, then it's more likely that my large language model is going to perform well if it hasn't seen this task. And of course, these are a lot of limitations, but as I was mentioning before, from GPT-3 and the following models also that we have seen last time, they generally do quite good at few shot learning. Also, so here I've added also on synthetic tasks, because one criticism could be, oh, I have a data set and GPT-3 is very good at few shot learning on it, but since they've scraped the entire internet to train it, it could be that somehow there was data leakage, because when scraping all the training data, somehow they found this data set, and therefore they maybe have even seen the test data set. But in that case, even if we make data up, so we create synthetic task, it still performs well on it. So the generalization, we're a bit more certain that the generalization capability is actually there. Right, so far we were talking about prompting. We were talking about fine-tuning more in the classical sense. But when it comes to prompting, there's no gradient update. We just use the language model to fill in the gaps. And so, of course, what's prompt-based fine-tuning? Well, that's just using LM prompts to get a lost signal. So am I predicting the right word for whatever the task is? And in this case, we don't have the classification head anymore, because we just let the language model predict. So we can do the update directly on the language model weights without having the layers on top. So this has two issues. First of all, multiple word verbalizers are quite complex, because of course if I'm trying to predict one word, then it's easy to, because that would be like one node in the output distribution of your language model, so you can back propagate from there. But when it's multiple words, that would actually imply multiple steps of prediction for the language model. And in those cases, it's really hard, like it becomes a bit more tricky. There are solutions, we're not going to get into them. But the point is, if you have multiple steps, does it really make sense to do like a, back propagation step on a word like was instead of like terrible? So that's when things get tricky. And the second point, as maybe some of you wants to guess, what's the issue with just prompt-based fine-tuning? So just recall, we're not propagating to the layers on top, we're propagating to the language model. So we're using the prompting to perform gradients updates on the language model itself. What was the thing that we were trying to get away from? There's like one even more apparent. So we talked about freezing layers earlier. What was the point of freezing layers? Exactly. Like the whole point was I don't want to update millions of parameters. I want to update maximum thousands. If I do this, then I'm back to updating a lot of parameters because I have to update, well, the whole bird, the whole whatever the language model is. Probably, yes. So there's for sure ways, there are ways to avoid overfitting, but again, if you're back to pretty much changing the whole model, you could lose the information that was learned in pre-training. There's always that risk, and that's why the layers on top are usually a safer choice. I mean, so the question is about versioning. Can I keep the just pre-trained model? And if the fine-tuned one doesn't look as good, then I go back to the older one? Yes, but then you have two versions, and it's really not clear which one is better. Whereas, like, there are probably solutions like, I mean, we're going to see in them in a second, but ideally you would like to improve your model without losing all the pre-training information. Because otherwise, either you have a pre-trained model or a model that is overfitting. And I think neither is good. Okay. So the issue, as we said, is, oh, okay, prompting's cool. We don't need layers on top, but now we're back to the issue, oh, we need to fine-tune the entire language model, probably worse than before. Are there ways to, have less parameters, but still use prompting? Because prompting is really cool, because we don't need to define a downstream task, well, loss, or well, whatever comes with a downstream task. And PET, which is a method that pretty much allows you to use few-shot learning, but still only update a normal, like let's say a small size model. And what you do here is that you have unlabeled samples, and then you have your, let's call bagging method, so just a set of large language models. Usually mass language models are pretty good at this. And you just let it predict, and then you take the soft labels, and whenever I say soft labels, I mean you take the probabilities of the output and not just like the argmax. And then you use the soft labels, you average them, and then you give them to a small classifier that is trained with the soft labels and also the same input. Meaning that the smaller model is in this distillation / teacher-student setting, and it's allowed to use the large language models as annotations, but then when I do gradient updates, I'm only doing gradient updates on the small classifier. And so I'm back to, I have the power of prompting, because I don't have any layers to fine-tune on top of the language models, and I'm only actually probably training from scratch a small classifier that can actually leverage multiple language models. And the nice thing about PET is that you can get GPT-3 level performance with something in the million of parameters, which is quite insane. And also it's extremely efficient. There have been extensions. For instance, one was iPad, where, you train your model, but then while training your model, you have also taken a lot of soft labels out of this language model. And this can be used to have then a larger data set. And then the larger data set could be used to create better mass language models, and then you repeat the procedure. This, of course, already requires a bit of a higher computational effort, but that's pretty much the idea. Mm-hmm. Because you're using prompting, so you're using basically the good side of large language models, but you're only doing updates on the smaller classifier that uses the soft labels, meaning that the large language models are not receiving any gradient update, and you're only applying it to the smaller one. So that's pretty much the answer. The fact that, so first of all, these you don't have to create. So if you were applying fine-tuning to this, first of all, you can only use one large language model. Okay. Second, the labels that you would get out of it wouldn't be soft. It will always be like hard labels. So it was like, okay, positive or negative. And whenever I change task, then I need to take completely other labels. Yeah. You could actually only the classifier, yes. Yes, but you cannot leverage multiple language models. Mm-hmm. Okay. So what's different is that the prediction part is also done by here it's done by the language model. Right? So if you think about traditional fine-tuning, the language model gives you a hidden representation, and that goes to the layers, which give you the label. Right? Here, you're using the language model directly to get the label, and then there's a classifier that is done on top of it. Yes, meaning that the language model is doing more of the heavy lifting as well. And we have seen that if few-shot learning is so good, then probably if we do the heavy lifting with the language model, performance is better. And that's why now you can achieve GPT-3 performance. Yeah? Was another question? So I do not know the question is, why are masked language models better at this than other, for instance, autoregressors? So what was the question? No, S1, S2, S3 are soft labels. So language models give you a probability distribution over the vocabulary, right? That's the output of a language model. And then you take the probabilities for the words that you care about. You just do a softmax or whatever function for normalizing, and those are your soft labels. Okay. All right. I think I need to, but maybe we'll get them at the end. Otherwise, it's really hard to continue. Okay, so the overall theme is, how do we continue in this direction of, yes, I do want to use large language models, but I want to keep reducing the amount of parameters that I want to update. So we have seen in context learning, I need like something in the billions in terms of model size, and I do not do any retraining, so that's good. Prompt-based fine-tuning, well, I can go slightly lower because I have some fine-tuning available, but I still need to retrain all the parameters. And then what's the next idea is, maybe I could update just some of the parameters of the large language model. So I leave maybe, hopefully more than 99% of them untouched. So they refer to pre-training. And then the less than the 1% refers to the task that I'm looking at. And this is called parameter efficient fine-tuning. And now we're looking at methods that fall in that category. So the first type is what I've called input modification, and here we have the two subcategories of prompt search and prompt tuning. And a very simple example of prompt search is when you're using ChatGPT and you're rewriting what you want in a different way, and you see that the answer of ChatGPT improves when you give it more details. And now these slides are pre-ChatGPT, but that's pretty much what it means. So prompt search wants to learn the language tokens in the prompt, so this is a discrete search, so that your performance gets better. And prompt tuning instead says, probably natural language doesn't give you the optimal prompt for your model. Let's just learn a continuous one. So it says the optimal prompt is not made of, an embedding that comes from words that are understandable to us. And we'll start with prompt search. Two methods in this area. So prompt search is also something you could do manually. And how do you do it? You try different prompts and you see what works the best. That would be probably what 99.9% of the people do. But let's say on a more, when you're scaling up things, there's something called auto prompt, which tries, so we were saying that in context learning, there are terms, and based on their frequency, it's easier for the model to locate the task within the pre-training knowledge that it has accumulated. And so using gradient guided search, you try to change trigger tokens. They're just tokens that are appended between the input and, well, the mask that you're trying to predict as output. And those trigger tokens should facilitate locating the task. And then an alternative approach is LMBFF, which takes models like T5 or other masked language models, and then you just have the input and you have the output word that you would like to get out, but you just let it complete basically the verbalizer around it. And by just letting it complete, you get templates for possible verbalizers, and once you have, well, a set to test, you just, well, test and see where the performance is the highest. And that's how you get a possible verbalizer. That's how you search for possibly better prompts to get higher performance. Okay, then prompt tuning. As I said, we are not looking for words that are ideal to have in the prompt, but rather we are looking for continuous vectors that even facilitate even more the language model to locate the task. So in this case, we have what we called placeholder tokens, which in this case is this red vector at the beginning of the input sentence, which is usually initialized with, well, a vocabulary instance. And then as the model performs few-shot learning or prompt-based tuning, then we're also going to backpropagate to this specific input vector. So over time, as the model performs the task, this input vector is going to change, and we'll change as you have for all the other weights in a better way so that the model has higher performance. But in this case, the rest of the language model is untouched. And then you say, oh, but what happens when I have a different input? Do I have a different placeholder token? And the answer is no. You actually keep using the same, given that you're doing the same task. So what do I do at inference time? I take the input that I care about. I attach this placeholder token that on top. And this placeholder token probably doesn't have any meaning, doesn't trace back to any word they're familiar with, but still works better for the language model. If you care about contextualization, meaning that this input should not only be dependent on the task, but also be dependent on the instance, then you can also learn the weights that depend on it. And that's exactly the image that we have here. So we backpropagate to that input placeholder and to the weights pretty much, let's say, on that trajectory in the language model. So it seems like, oh, but those are already a lot of weights. Yes, they're a bit more, but still we're talking 1% of the entire model. Right. Maybe now we can take a few questions. So hands up. There was one question right here before. Mm-hmm. Mm-hmm. S1 will be the probability for terrible and the probability for great. So that's why they're called soft labels. With their probabilities, yes. The same thing, but from another language model. Yeah. There was a question up there, I think. Yeah. Mm-hmm. So that's what I was saying before. It's not like 100% understood why, for instance, in this case, the word atmosphere will facilitate the performance on this specific task. very likely is that the word atmosphere is a trigger word, meaning that it has a very high frequency in this case, in sentiment analysis task. For instance, oh, there was a good atmosphere, there was a bad atmosphere. And just the fact of including that in the prompt as a trigger token pushes up performance. That's all it is. It's just like a help for the model, because whenever we see atmosphere, the attention mask is going to recognize it and will locate probably the task that it's performing in its pre-training space. One more question? Yeah. So prompt search, probably this is the best slide. So for instance, in this case, with prompt search, I am doing prompt-based fine-tuning, but I'm not updating any of the model's weight. The only thing that I'm updating is which are the ideal tokens in the input that I use as, well, pattern or verbalizer. This is a case with a verbalizer. So I'm fine-tuning that it was. Now, question is, oh, but when we do updates, we do it in a continuous space. How can we always get words? You have to use tricks to rediscretize, for instance, nearest neighbor. Prompt tuning, on the other hand, we lose this notion that the ideal prompt has to be made of words, because perhaps human words are not the most optimal way for the model to locate the task. So what we say, forget verbalizers, let's just put like a placeholder token and let it do the magic. This is pretty much the idea behind it. So when we do fine-tuning, this vector is just going to do whatever it wants, and of course it's going to get optimized by gradient descent, and it's not going to trace back to any word that exists in natural language. That is the difference. So tuning is continuous. Search, you're still working on the discrete space. Search, you're finding words. Tuning, you find, well, an embedding of a potential word that, however, doesn't exist. I mean, they're just like, they work in completely different space. In tuning, you don't have any discretization step. It's not more abstract, just we don't care about going back to actual words. That's the main difference. Yeah. You can have any setting that determines your loss, yes. I would say, yeah, this is like prompt-based fine-tuning, but I would say any setting that gives you a loss, this is more like to what do I propagate it. That's the difference there. Yes, we've talked about this. Prompt tuning, we've talked. Okay, so those were methods that work on, I want to optimize the performance of my model by changing the input. And that's a way to not update weights. That's a cool strategy. So BitFit is instead of a parameter efficient fine-tuning method that instead looks at the model weights. And for instance, we update only the bias term in the self-attention that we have in transformer blocks. And those are, of course, a much smaller subset of all the weights. And the nice thing there is that, again, with I think 0.1% of the weights to update, you still get pretty much the same performance as you would get with the total fine-tuning. Then something that we've actually used a lot, adapters. So here, imagine you have transformer blocks. What you do, you add layers for each transformer block that do not get updated at pre-training time. Maybe they were not even there. And then when you do the fine-tuning, you freeze all the rest, and you just train these adapter layers. Now, and here will come the question, but what's then the difference with just freezing? The main difference is that these are layers that are specifically made for being fine-tuned. When you add layers on top, there's nothing specifically constructed to reduce dimensionality and have less parameters. So usually adapters, by being at various layers of the transformers and having this down projection and up projection, they're able to have not a lot of weights, and they also influence the transformer at several levels of feature extraction. And that's why they just work a lot better than simply, oh, I'm gonna freeze my model and then update the layers on top. Of course, you need different adapters for each task that you're doing. That still stays. So as I said, we add feed-forward layers and skip connections after each feed-forward layer of the transformer. We have down and up projection to reduce parameters, so the transformation is done at a lower dimension, which means, well, less weights. And then once the pre-training is done, we only touch the adapter blocks when we need to learn a new task. And here I've added, for those of you who are really interested, there's an even more advanced version, which are called compactors. And the trick there is they manage to have even less weights. Last one, IA cube, which pretty much has the same logic of the adapters. So when we pre-train the model, we have nothing there. And then we apply this element-wise rescaling once we want to learn the new task. And we do that by applying scalar multiplication, so element-wise multiplications at the attention level. So for instance, here, we, during fine-tuning, we learn these three vectors, LK, LV, and LFF, with the propagation as you know it. And then we're gonna, well, freeze them at inference time as well. And at that point, the LK and LV will pretty much influence the activation process of your model, and then LFF influences the forward pass that comes after it. And really the main message here is that each task you're learning will have its associated learned vectors that modify the way the model attends to different tokens. And that's how the model pretty much adapts to different tasks that it has not seen. This is a small comparison to make you understand. So we've looked at, so here we also have compactors, but there is bitfit, adapters, and also IA cube. And of course, the two metrics across which you always compare is, okay, what's the accuracy that I could get versus how many parameters did I have to change? So of course, the ideal case here, it would be like, you'd like to be as up as possible, but also as left as possible, because that means, oh, I could actually get higher performance than retraining all parameters while changing, well, ideally even the 0.001% of them. All right. So what have we seen so far? We have seen what prompting is, how that's used for in-context learning. So there was no update to that point. Then we've gone to prompt-based fine-tuning. So cool, we're still using just a language model, which is a lot better, but too many parameters. Then we delved into, oh, I still want to use a large language model, but I want to update the least amount of the parameters. And that's pretty much what led us to all the parameter efficient tuning. Before we jump into like multitask, I think there was a question here in front. No? Okay, someone has raised. You raised your hand? No, okay. Okay, so the thing that we keep seeing is, okay, we can use the model to learn a new task, but the question stays, why are large language models the ones that are so good at so many tasks? And as we've seen, in-context learning provides information to language models to locate a task, but we do it, well, I wouldn't say inherently, but at least implicitly. What if instead we also say explicitly what the task is? So I don't say, oh, the movie was beautiful, and then I need to predict, oh, this was positive or negative sentiment, but rather, please classify the following sentence as either positive or negative. And that is pretty much the idea of, don't I have a slide about meta learning here? Okay, we'll get to that in a second, but the idea is the same. So let's not give an example, let's give the actual task. So for instance, a transformer that was trained on with this strategy is TK instruct, where not only you give the demonstration, but you pass specifically the task together in the prompt. And of course, this lets you leverage many tasks at the same time, because then, well, I don't even need to come up with a lot of examples, but I can just have the task description and just a few examples. And of course, good strategies to perform proper learning would be you should group tasks by types. For each task, you should have multiple prompts. You should hold out certain tasks for evaluation. And ideally, unseen tasks belong to the same type, so that when we test on a task that is unseen, the model has not seen yet a task that is at least on the similar type. So that would be like true few shot. This is just a list of data sets that provide a task together with task types and also the number of instructions per task, because as we said, even for the same task, you could have even different prompts that explain that task. And P3 is a very known data set that pretty much collects prompts for different tasks. So for instance, in this case, it has 183 data sets. So a data set will have a task and data points. And then it has 2085 prompts that pretty much explain the model how to perform that task. And what we have seen so far is that if we have more tasks, it helps, because then there's more that the model has seen. Larger models helps, and this is pretty much clear by now, because then we have more memory available to locate that task. But what's been seen is that more instances for task do not help. Meaning that if I tell you, could you please perform this task, and I give it 2 instances, it doesn't really seem to make much of a difference if I provide it with 20. Or at least like not as much as it would mean, it would matter if I improved, if I had a greater size of the model, or if I had more tasks available. One last thing in providing the task, also the answers can matter. And probably by the definition, or by like the way that you formulate an answer, you can actually see the same behavior in the answer of the model. And an example is the chain of thought. So if whenever I have a question, a patterned input, and I take the verbalizer, if the verbalizer also contains reasoning on how to get to that answer, the model is more likely to do the same in its answer, because the location process is altered. So in this case, I can have a problem about counting tennis balls, and if instead of saying that the answer is just 11, I say, well, that's how I got to 11, it's more likely that the model will locate a way to formulate the answer that is similar to that. And of course, this first instance here would be the demonstration, and this is, the pattern, and this is like the new, the verbalizer, sorry, it would be just like the answer is, but then it tends to put this on top if you give it the freedom to do it. Okay, and of course, what's the biggest pro of this is that you get sort of an explanation. I mean, that's the model that's the explanation that the model gives you. There's no way to check if that explanation was just made up because it's plausible, or whether that's actually the logical reasoning that was followed. And yes, this is what I was pointing at earlier. So why does zero shot or few shot only work on large language models? As we said, is because the larger they are, the more likely they are to store information about many things that I have seen at pre-training time. Means that I can retrieve it, means that we perform well. And the idea for meta-learning is, okay, what if instead of doing it implicitly during pre-training, we do it explicitly? So I'm not gonna crawl the internet and just like make this huge piece of text that I'm gonna pass to my language model, but rather I'm gonna structure it in tasks and samples that belong to those tasks. And meta-learning is something that we also cover more in detail in the next block, but we'll talk about it briefly as well now. So meta-learning is this additional training stage that you do after pre-training. It can potentially also be the only training stage, so you don't do pre-training at all, but you start directly from meta-learning, and as we said, is a more structured pre-training for your language model. And The reason why it could work on smaller models is because by structuring the information that the model has seen, you might need less of it. Because so you don't need those immense corpuses to make sure that the model has encountered all the things that you actually care about, but rather you provide them explicitly. And of course, the problem that you have is that, okay, but now, well, when I have pre-training, it's easy because the model just sees a lot of text and it's going to learn all the tasks implicitly. But if I want to do it in a structured way, there's so many tasks that somehow they need to converge to the same format, and that's of course not an easy thing. And a simple strategy that is used in meta-learning to find a common template is, for instance, UniFew can look at all classification tasks that either have 2, 5, 10 labels that even differ, and you just formulate it as a multiple choice exam. So it's pretty much your model's playing Who Wants to Be a Millionaire by having a list of possible classes and having to choose the right one. And the nice thing about this setting is that, well, you can formulate every task in exactly the same way. I'm going to have my input, I'm going to have the classes that I have as a choice, and the model has to choose one. And in this way, I can train a model not on a classification task, but on all classification tasks at the same time. And since I'm doing it with meta-learning, I don't need to do like those massive pre-training steps, but it's going to also work at a smaller scale because of its structure. And an instance of this, yes? Yeah. So T5, the question is, how is this different from T5? T5 was also appending prefixes depending on the task. The point is, it was not as structured as meta-learning. And like when T5 came out, we didn't have those datasets available that we have now that are able to have this template for multiple tasks, which really make what's now known as meta-learning. And that's what T0 is. So T0, which is, let's say, the next level T5, is literally T5 plus meta-learning by mixing samples from many NLP datasets. And of course, in this case, you will have a unified templated format. And for each format that puts in common several datasets, you will also have multiple prompts. And the nice thing is that now, thanks to meta-learning, we can have a model which is just 11 billions, which means is more than 10 times smaller than GPT-3. And it still outperforms it on unseen tasks. And the reason why it does it, as once more, is because of the structure that is applied in meta-learning versus the, well, unstructured way of actually training in a pre-training setting. Yes, and of course, we've been talking about a few different things. So there's few shot, there's parameter efficient tuning. There's a lot of ways that you can fine-tune a model, but to evaluate them is really hard. And we're going to see how to do it, but especially we're going to see why it's so hard to do it, especially in the few shot setting. So let's say I have different versions of GPT-3, and I'm like, oh, they have been trained in a slightly different setting. Which one is the best? The problem is that when you have so few examples, your variance goes up by a lot, because if I'm choosing 3 demonstrations versus 3 other demonstrations, I probably have so many demonstrations available that the number of sets for those 3 is huge, meaning that the variance that you're going to experience is pretty large. And also, whenever you change tasks slightly, the thing might be completely different. And this introduces a lot of complexity, which is really hard to deal with. Plus, there's one more problem. The problem is, okay, what if I really have 50 instances of GPT-3, and then I try to fine-tune them in a different way through few shot, or maybe I just check the performance through few shot. Is this really few shot anymore? And the answer is not really, because if I then pick the model instance that is so good, or that is better than the others, but choosing from many, many variants, I'm actually using those data points to choose my validation set. Which means that this is not really few-shot learning anymore. Because what we've said about few-shot learning is I want to fine-tune using a few samples. And if those samples influence the validation set, or like the model that I pick, then, well, I'm using definitely more than few. And also from a philosophical perspective, if you want, when we talk, like the reason behind few-shot is humans are able to perform few-shot, so should models. And of course, the way that few shots is performed by humans is not by having 50 copies of myself, and then we're gonna pick the one that specifically does that task better. But rather, well, I should be able to perform any task well only by having one version of me and only one validation set for few shot. And that's why also they get distinguished here. So we have the traditional setting, which is just a fine-tuning as we talked about in the beginning. So it's the data-rich supervised setting, which doesn't have many trained distributions. When you went to like machine learning, probably you were training a model for one specific task. So you only had one trained distribution. You had many train examples, and you also had many validation examples. The meta-learning, which is what we've seen later today, applies the same thing, but with less training examples, but more task examples. So in this case, we have many training distributions. We don't have many train examples, and we also don't have many validation examples. Then we have what we've called few-shot learning so far, but as we said now, not really. So we don't have many train distributions. Obviously, we have actually zero, or let's say few for locating. We don't have many train distributions because the entire distribution is found out by the pre-training. Then, as I said, we don't have many train examples because it's, well, we just have a few demonstrations. But then we have many validation examples if I then choose the model that performs the best based on these 3 examples that I'm giving it. And then there is like the true few shot, like what we really mean should be comparable to humans is you don't have many train distributions, you don't have many train examples, and you don't have many validation examples, meaning that you train the model in an unstructured way and it should just work. And this is, of course, really hard. You probably need a massive size to do it, and that's why we have to balance it out with finding strategies like meta-learning or, well, finding having many validations data sets. And of course, when, yes? You actually have both cases. You could have different versions of the models that are tested on the same, well, prompt or like demonstrations, which is your validation data set in this case. Or you could have the same model and you're testing many different. And this could be applied to any of the parameters. And one is. This could be the case of having many models testing on the same validation set. So on the same, for instance, set of examples of demonstrations. It's true. So, you're right. So it has to be the other way. So you're testing. So the validation sets need to change a lot. Exactly. Yeah. So you would have one. The reason is you do have the same set of validations examples, but for one task. When you change the task, you're going to have another one. Yes, it's meant in that way. Yes. So normally, when you measure the accuracy of a model, you measure it for the instance level generalization, meaning I have a trained data set, I have a test data set. How am I able to generalize from the first to the second? And this is, of course, instance level because it's always the same task. So how do I go from scene to unseen samples? And of course, cross-task generalization is, okay, now I don't want to go from from sample to sample within the same task, but also across tasks. And one metric that is used quite a lot is the RG, which pretty much measures the performance gain and loss, because usually when you get better at one task, it's likely that you get worse at others. and you basically average the two results, and that's pretty much how you get the overall model improvement across multiple tasks, which is something quite important in, for instance, meta-learning. Because meta-learning, you're facing all tasks at once in this unified template, and of course, ideally you would like to see model performance going up across all of them. Never really happens, but at least on average, that should be positive. And for these, there are also data sets. So data sets that have, I mean, they're all quite similar, but they have different tasks, and they're put together in types, and they're used also as benchmarks to check against meta-learning and other settings where the number of tasks actually becomes more important than the number of samples, which is often the case for few-shot learning. Like, I don't care about saying, oh, I'm good this much across 2,000 samples, but oh, I'm good this much across hundreds of tasks. And yeah, that was a lot of information. As you see, the idea today is we wanted to get rid of things that are on top of language models, because language models are just a lot better. So point one was to transform objectives of whatever the downstream task is to the language model objective. Point two is we do not want to touch all the weights of the language model, because that would be, computationally speaking, a mess. And third point is we want to leverage the knowledge that language models have acquired through pre-training to not have to do so much work when we work on downstream tasks. And then we had the thought of, oh, how do we really need to go necessarily big with language models? And the answer is yes, if your training procedure is unstructured, which is the classical pre-training, but meta-learning allows you to bring down the scale if you have a unified template that can describe a lot of tasks. And yes, and so all of this is put down, of course, under the umbrella term of, well, fine-tuning, which is possibly what approaches of how do I use these language models for, well, specific downstream tasks. Yeah, so these are the main references that I recommend. As always, we have the three approaches, the minimal being working with the slides, standard, especially reference 1, I think is quite relevant, as is one of the tutorials of the main NLP conference last year. So that was pre-ChatGPT, but still covers definitely a lot, and also a lot more than what we've done today. And then, of course, the in-depth would be the same, but actually going through those 400 slides. Yeah, and otherwise, thank you, and we'll have the last lecture of the block next Monday, yes.